we are going to speak about solidification. Now there is one really big difference between solidification and the phenomena that we have studied before, both in the magnetic model and in the phase separation problem. We have been able to identify a variable that was called an order parameter. In the case of the magnetic model, this was the magnetization. In the case of phase separation, it was the concentration. And then we have derived the Ginzburg-Landau functional in that variable. And the free energy had a double well structure. And in both cases, these models exhibited a phase transition with a critical point that is above a certain phase transition, about a certain temperature. There was a single phase with a single minimum corresponding to zero magnetization in the magnetic model, or corresponding to a completely miscible substance in the phase separation problem. And below the critical temperature, there was a coexistence between two phases, right? And these phases had different compositions. Now, solidification, in what is this different? Solidification is different in the sense that for solidification there is no critical point. Okay? So what's the nature of a critical point? If you think about the magnetic model, say if you want to bring it from the plus phase in the minus phase, of course you can apply a magnetic field and then you will brutally jump from one well to the other. So going for, this direct path from the plus to the minus phase, so say, you will have to get across a phase transition line, the phase transition between the plus and the minus line. But you can also do this differently. You can start from the plus phase, then you can heat up the system. When you are above the critical temperature, there is no more phase transition, so you can change the magnetization, and then you can cool it down, and you end up in the minus phase. So if you go along this path, you will never encounter a phase transition. Okay? This is the same, as you might remember, we haven't talked about this, but it could be treated with exactly the same formalism. This is the same for the liquid-gas transition. Okay? You know maybe that there is something called supercritical liquid. That is, if you take a vapor, and of course, if you cool it down, it will condensate, and you will have the phase transition between gas and liquid. But instead of that, you can also first compress it to go to very high pressure, then cool it down, and then release the pressure, and then you will get to the liquid without ever encountering phase transition, because, well, I remember, as you remember maybe, the phase diagram of water. Normally you draw it with temperature here and with pressure here. So here is solid, here is liquid, and here is vapor. You remember this phase diagram? Probably everybody has seen it. So these are two intensive variables, T and P. And what I have just said, if you are sitting here in the vapor, if you're cooling it down directly, you go across this phase transition line and you end up in the liquid. But instead of this, you can first heat up and increase the pressure. Then you can cool it down, and then you can release the pressure, and then you can come here without encountering any phase transition. Okay? And this is because this phase transition line ends here at a critical point, which is just the same as for the magnetic problem and the phase transition problem, the phase separation problem. Because in both cases we found that we had a Ginzburg-Landau free energy that had a transition between the single well and the double well structure. Okay? Now, solidification is different in what sense? Well, you see here, there is this phase transition line, for example, between solid liquid and here between solid and vapor. Is this correct, this diagram? Oh, yeah. Anyway, you can see that this solid liquid or solid vapor transition has no critical point. Okay, so you cannot do the same thing as for the liquid vapor transition. You cannot go from the solid to a vapor or from the solid to the liquid without going through a phase transition. Okay? And this is because, for some fundamental reasons, because in the crystal you have a crystal structure, okay, which is a breaking of the translational invariance. Whereas here in the liquid you have a disordered structure, and somehow this symmetry breaking can never be circumvented in some sense. So you cannot go from the solid to the liquid without having a phase transition. Now, what is the consequence in practical terms, and what is the difference between that and what we have seen so far? You see, the double well function describes two different phases, either plus or minus, or the concentrated and dilute phase in the phase separation problem, with the help of the same variable and with one single free energy function. Okay? Here, in the solidification problem, clearly, we have two different phases that are not described, cannot be linked by a continuous path. So we need two distinct free energy functions. We need one free energy function for the solid and another free energy function for the liquid. So we have two separate free energy functions. And well, since I will not always talk of solid and liquid, because I will also talk sometimes about alloys, I will just generically call two phases alpha and beta. And I will first talk a little bit about the coexistence of phases alpha and beta, and you will see that we will find again a lot of things that we have seen during the last 2 days. Before I go into that, maybe another comment. You might remember from my very first lecture, the second or third transparency that I showed was the transparency with the three different length scales, microscopic, macroscopic, and mesoscopic. And at that time, I told you that there are sort of two viewpoints on phase field modeling, the bottom-up view and the top-down view. So up to now, we have mainly taken the bottom-up view. You have seen that both for the Ising model and for the phase separation problem, I started from some microscopic model, that is the Ising model or the lattice alloy model, and then I have done successive approximations to come to the Allen-Kahn and the Kahn-Hilliard equation. So that's a typical examples for the bottom-up approach. Today, I'm going to show you the example of the top-down approach. That means what I'm going to do first is I'm going to explain to you the traditional formulation of solidification problems as free boundary problems. Okay? So I will explain you a little bit how you can properly define the equations for interfaces in these sharp interface pictures, and how you can write down and justify these sharp interface equations, and then we can see how this can be in some sense implemented or solved by phase field equations. Okay? So first I'm going to to talk with you a little bit about the physics of interfaces when two phases are in coexistence. And I will set some conventions that we'll use all the way today. So first of all, I will make one very important assumption. I will assume the molar volume is constant. What do I mean by constant? That means it is independent of the phase and independent of composition. Now, you can object legitimately that both of this is not true. Okay? You know, for example, in water, solid water, ice, has a higher volume as the liquid water it freezes from. This is kind of anomalous for most substances. The solid occupies a smaller volume than the liquid. So there is a volume change upon the phase transition. Also, if you have a mixture, normally one sort of atoms is bigger than the other. So if you have a concentrated mixture in the big atoms, then this will have a larger volume than if you have a mixture that is depleted in the big atoms. So in general, this is not true. Now, why do I make this assumption nevertheless? it's if you don't make it, you are actually in big trouble. And how to write down this kind of models in this case where the volume changes is still quite an open research question. And why are we in trouble and why is this difficult? Actually, if your volume changes, you cannot do with a simple diffusion equation as a transport equation. This is very intuitive. For example, if you think about the freezing, if you start to form an ice crystal in liquid water, well, the ice crystal is expanding, so you have to push some water out. Or alternatively, you have probably all seen if you put the bottle with water in the freezer, well, at some point the bottle will break because the ice is expanding. So if you take into account this volume change, you have to solve a mechanical problem with it. Either a problem of fluid flow if you have the fluid pushed out, or a problem of elasticity if you have some confining vessel. But you cannot capture the physics correctly without taking into account the mechanics. Okay? And that's why if you want to take into account a change in molar volume, you immediately and very fundamentally get a problem in which diffusion and mechanics are coupled, and this is complicated. So there are very interesting questions concerning this to be addressed, but I will evacuate all this. I wanted just to tell you this, just to say that this is not a finished field and there is a lot of things to do left for you. So, but if the molar volume is constant, this has also a few very inconvenient consequences, because you have seen that our free energy functions are normally volume integrals, right? There's an integral over space. So if the molar volume is constant, it's very easy to define consistently various densities. So for example, if the molar volume is constant, the natural thermodynamic potential that I'm going to use is the free energy, because it's a function of volume. Okay? But you see, one of the nice consequences if the molar volume is constant is actually it doesn't really make a difference if you use F, the free energy, or G, the free enthalpy, or the Gibbs free energy. Why is that? Because which means that F and G are just proportional to each other. Okay? So in many papers you will see that people write down phase field models using the Gibbs free energy G and not the Helmholtz free energy F, which in principle is a problem, because if you write down a Gibbs free energy, the volume is not fixed. So how would you define volume integrals, right? Seems quite paradoxical. But actually in all these papers, somewhere implicitly, people make this assumption. Sometimes it's stated, most of the time it's not stated, but just think of, if nothing is stated, you can think that people make this assumption, and if people make this assumption, then taking F or G doesn't make a difference. Okay? So, since I'm used mostly to F, I'm going to continue to work in F and not in G. So, if I have some extensive quantities like the free energy, the number of particles, okay, I can form volume densities. So I can form the little f, which will be f by v, and I will define that rho is a number density, that is the number of particles by unit volume. And so I will define a rho bar, which is just the quantity that I have introduced before, that is the Avogadro number times divided by the molar volume. So this is just the constant number density in this mixture. Now, if I have a mixture of k components, of course I have numbers n1 until nk of particles. So I will also have number density ρ1 to ρk, which are of course the number density. Okay? let's come to a few consequences of this. So I'm talking about the coexistence of two arbitrary phases alpha and beta. How can I describe this coexistence? You know, at coexistence, intensive variables are the same in both phases. We have seen this on the first day for the temperature. The temperature homogenizes when there is a thermal contact. We have seen it yesterday for the chemical potential. So what are the intensive variables? Those are the temperature, the chemical potentials of the various species, and of course you also have the pressure, because this describes mechanical equilibrium. Oh, okay. I should maybe add that here I'm speaking about two phases separated by a bladder interface. We will see right next what difference it makes when the interface is curved. Okay, so these are our constants, and I have already given you yesterday an expression for the pressure in terms of what is called the ground potential. So the ground potential omega for a multi-component system is given by F minus sum of from I equal to 1 to k over all the components, mu I n I. Okay? And I have already told you that this is equal to minus PV, pressure times the volume. So if I divide through by the volume, that means if I define the grand potential density by omega by V, so this is equal to F minus sum over I mu I rho I. This is just equal to the negative of the pressure. Okay, so let's do the two special cases that will be of interest for us today. So A, if I have a pure substance, that means K equal to 1, only one component. That means that I have only one number density, rho 1, and this must be equal to rho bar. Okay? So if I apply this equation that the pressures in the two phases must be the same, what do I get? I get F alpha minus mu rho bar is equal to F beta minus mu rho bar. Remember, there is only one chemical potential. I omit the index, and the density is proportional to rho bar. So this falls out. So you get that the free energy densities are the same. Not very surprising. Probably you already knew that. Just keep in mind that this hinges on the fact that I assume that the solid and the liquid have the same volume. Okay? If you relax this assumption, strictly speaking, it's not true. Okay, now slightly more interesting. A binary mixture. What do I get here? So I get that F alpha minus mu 1 rho 1 alpha minus mu 2 rho 2 alpha is equal to F beta minus mu 1 rho 1 beta minus mu 2 rho 2 beta. That's the general expression for the gas potentials, so for the pressure. Now, of course, I can use that my two densities are not independent, so I can pose that rho I will call rho 2, and then I will have that rho 1 is equal to rho bar minus rho. Okay. If I plug this in, what do I get? I get F alpha minus, and then I get mu2 minus mu1 rho. And then I have left here minus mu1 rho bar is equal to, and all this taken at the alpha phase, equal to F beta minus mu2 minus mu1 rho beta minus mu1 bar. Okay, this comes just because I eliminate rho 1 here. So that's where the mu1 rho bar comes from. And because of the minus sign, I get the minus sign here. So you see that this falls out again. And what do I get in the end? I get that F alpha minus mu2 minus mu1 rho alpha is equal to F beta minus mu2 minus mu1 rho beta. We have seen this formula yesterday for the lattice alloy model. So this, yesterday I have, for simplicity, simply called mu. Okay, and I've called it the diffusion potential. Okay, because as we have seen, this potential drives the diffusion currents, and diffusion currents correspond to the exchange of A and B atoms. So that's why this is called the diffusion potential. So I will follow probably the same convention and just calculate, call this mu. And this function f minus mu rho, I will call it in the following little omega. So once again, as stated yesterday, this is not strictly speaking the grand potential, because the grand potential is this. But since we have this constraint of molar volume, it just behaves exactly as grand potential. And a very important thing is this equation. If you have two-phase coexistence, these grand potentials must be the same as the two phases. Okay. So you see that this is perfectly general. It's not limited to the lattice alloy model. It's the case as soon as you assume a constant molar volume. Okay. So let us now talk a little bit about sharp interface models, right? So I have told you, if I have the coexistence of two phases, intensive variables are the same on the two sides of the interface. On the other hand, extensive variables can vary from one side of the interface to the other. Okay? Now, a very simple example where you can see this is to consider, say, the liquid-vapor transition. Okay, so you have a droplet of liquid immersed in its vapor. Why this is particularly intuitive? Because then you can think about the density. Okay, so the number density. The number density is clearly varying in space. So if here I plot rho as a function of x, so here will be the liquid, where the number density is large, and here will be the vapor, where the number density is low. So you can clearly see that there must be a jump between the two. First, another remark. Usually, if you think about the number density, if you look at your sort of primitive definition of what's an extensive variable, you would not call the number density an extensive variable, because if you change the system size, keeping the same condition, The number density is not going to change. The total number is going to change, but not the number density. So you could get a certain confusion and think the number density, in fact, is an intensive variable. No, this is not the case. It's the density of an extensive variable. And the difference between the two you can precisely see from the fact that this quantity has a jump in the interface. This is only possible if it's the density of an extensive variable. An intensive variable always is constant in the interface. Okay? So it's an important difference because often you explain the difference between intensive and extensive variables hand-wavingly by the fact intensive variables are those who don't change when you change the system size, and extensive variables are those who change. You need to be a little careful with that. But so here you have a quantity, an extensive quantity like the density that has variation through the interface. And actually, why did I draw this profile? And if you look at some microscopic simulations of this situation, like a molecular dynamics simulation of a liquid droplet immersed in a vapor, you can see that the situation is really like that. I mean, the interface is rough and diffuse on the microscopic scale, so the density doesn't sharply jump from the liquid to the vapor value. There is really a smooth variation like this. Okay? We'll see another picture of molecular dynamics simulation of a solid-liquid interface in just a few moments. And we will see that for solid-liquid interfaces, generally, they have this structure as well. So then, if I want to make a sharp interface theory, that means if I want to assign an exact position to that interface, you may ask the question, how can I do that? Because, okay, well, there is a continuous variation of this density. Of course, I could define the interface by the point where it crosses a certain value, but then the interface position would depend on the choice of that particular value, so this is not very satisfying. So there is a sort of rigorous way to define an interface position here, and this is what is the so-called Gibbs construction. So what you see is, if I want to obtain the total number of particles n, I have to do a volume integral over rho of x dx over the whole system. So say I integrate from 0 to L. Right? So I integrate the surface under this profile. This will give me the total number of particles in my system. And now I can consider a fictitious profile where this here is the density in the alpha phase, and this here is the density in the beta phase. So here this is rho, and here that would be rho beta. And now I can imagine that I can compare this system to a system with a step profile. Okay? So I suppose that there is a sharp jump here at some position x int. Okay, so I can again calculate the number of particles in my system, and now I don't need to calculate an integral. This is just rho alpha times x int plus rho beta times L minus x int. I put a tilde here because this is the number of particles that would be in the system that has this dashed profile. So this is perfectly well defined because rho alpha and rho beta I can read off from the phase diagram. So there's no ambiguity in alpha and beta. And now you can see that if I require that I get back the same number of particles, so if I require that this number of particles is equal to the true number of particles, then this becomes an equation for x int. Because it's the only unknown. I suppose that I know this profile, so I can calculate the integral. Here, everything is known except x int. So, in this case, I can define the interface position. So this is a rigorous method to define the interface position. It always works, except in one case. Can anybody imagine when it doesn't work? It's a kind of difficult question, but maybe somebody can find when it doesn't work. I will make you a drawing, and it will become obvious. Say I have some quantity here, which for the moment I don't. Oh well, I can call it rho. I can tell you what's the physical situation that this profile corresponds to. Okay, so what's the difference here? I'm in a situation where this density is exactly the same on the two sides of the boundary, right? So what is a physical case that corresponds to this? That would be, for example, in a binary alloy, you know that there is a phenomenon called grain boundary segregation. So if you have impurities in a polycrystalline alloy, they will tend to accumulate in the grain boundaries. So if I trace the concentration of impurities across a grain boundary, I will get a picture like this. So here this would be grain 1, this would be grain 2, and this would be the grain boundary. Okay? So if the system in equilibrium, of course, the bulk concentration of impurities in both grains is the same. And then this doesn't work to define the grain boundary position, okay? Because then this doesn't work because here the Xim just falls out. Okay. But in this situation, I get another benefit because this construction can rigorously define me what is called the grain boundary absorption. That is, I can define the excess of impurities that I find per unit length of grain boundary or per unit surface of grain boundary, which is just the surface area in between the two curves. This is the true number of particles in the system, the integral of the true profile, whereas this would be the number of particles if there was no grain boundary. And so the difference is just what is called the grain boundary adsorption. That is the excess of impurities that I have in my system due to the presence of the grain boundary. Okay? Now, this is actually very important because this also allows you to have a rigorous definition, rigorous and general definition of the surface energy. Because for this you can just apply the same thing. Because the thermodynamic potential is an energy, so it's an extensive quantity. And if you think, for example, now about the solid-liquid interface in a pure substance, in the pure substance I have just mentioned, F, the free energy density, is the same in solid and liquid. So I can draw exactly the same plot for F. So this is, if it's rho, then I'm in grains. If it's F, I'm in solid, say, and liquid of a pure substance. But the plot is exactly the same. On both sides of the interfaces, I have a certain free energy. In the interface, I have an excess free energy. So the free energy is higher because atoms in the interface feel uncomfortable in some sense because they would like to be either solid or liquid. They are neither, so they have an additional energy cost. So this is the surface tension is the area that is between these two curves. And in this way, you can define it rigorously for any system. Okay? Just a word of caution, it took me a long time to understand this because it's never well explained in the literature. Because people in the literature often say the surface tension is the excess free energy. Okay. Now, if you look at alloys, what's the excess free energy? Well, this question is sort of loosely stated, because indeed, if you speak about the free energy density, you cannot define an excess free energy for a mixture. Why not? Because in a mixture, the free energy of two phases is not the same. Okay? The free energy looks like this. Okay? It has one value on one side and another value on the other side. So you can use this maybe to define the interface position, but you cannot use this to define the interface excess. We have just seen a few minutes ago that the quantity that is the same on both sides of the interface for a binary mixture is F minus mu rho. So this little function omega. So if I'm in a mixture, actually I have to define the surface tension not as the excess of the potential F, but as the excess of the function omega, which is F minus mu rho. Okay? You can still call that excess free energy because the names for these sort of more complicated potentials are often not very well defined, but I just tell you this word of caution. If you see interface free energy, you have really to think, well, what free energy people need? Helmholtz free energy, Gibbs free energy, grand canonical free energy, or whatever. Just be aware that excess free energy doesn't necessarily mean excess of F or G. Okay? It's the excess of the thermodynamic potential that is the same in the two phases. Very important because that's the only valid starting point. So for a mixture, here this would be the function omega, and the same in the solid and in the liquid, omega is the same. In the interfacial region there will be an excess, and that's what's giving you the surface energy. Yes? Yes? Well, that depends on your boundary conditions. If you fix the density or the chemical potential, then you will just draw in more particles. If you fix the total number of particles, yes, then the bulk concentration will go down. Yes. Okay, so we have learned how to define rigorously the interface position. We have defined rigorously how to define the surface excess energy. Let's look now at two effects that will be important for the remainder of my talk, and that we have already seen in the context of the magnetic model and the phase separation. First, I'm going.
Any short questions?
Yes.
Since we have fixed the volume constant and we are doing everything.
Yes.
As of years, we have asked if the volume is allowed to change, whether what effect will be under whether it will increase or decrease.
Well, in the diffusive motion, actually, the center of gravity of the system remains in the same position. You just exchange atoms within your little fluid package. Okay? If you have a change in density, then you have to move the whole fluid package. Describe the motion of particles within their frame of reference, which is the frame of the center of gravity. If I need to take into account stretching and shrinking, then I need to have, in addition, an equation for the motion of this center of gravity. And then on top of that, I have to write the diffusion equation. So it's a coupled diffusion and fluid flow equation, together with phase change. As I said, well, if you can piece together a really consistent model of this, you can publish it. Because I would not really know where to find this. I would maybe know how to construct one, but since I don't like to integrate the hydrodynamic equations, because it's hard, and there's plenty of interesting problems to do where this is a good approximation, I've never done it. Okay, but it's, again, if you want to do it rigorously, it's not a small thing. Yes? Yes?
That will be like, see, dissipation of the energy.
Yes.
So that means it is a material dependent in terms of
Yes.
conductivity kind of.
It's material dependent, and it's really an interface property. So it's like you see the interface actually is physically characterized by two things. It's the surface energy and the surface mobility. Okay? And both of these quantities you will not be able to get out from a phase field model, because as I have said, phase field model is a mean field description, so it's not very accurate quantitatively. So these two quantities you have to get your information from in a different manner, either by measuring it or by doing some more atomistic simulation. Okay, we'll see an example a little bit later where we have done a coupling, where we've extracted these quantities, surface energy and surface mobility, from molecular dynamics simulation, and then we have put this into the phase field model. But this is really, I mean, the gamma in the mu k is really a material dependent property, and it can be even dependent on the orientation of the interface.
Irrespective of binary or multi-element also, this will be the same rule. The mu k is to dissipate the energy.
Yes, there is one mu k because you have one interface. Okay, in the multi-component case, there is of course more equations, but there is only one mu k. Okay? But this mu k also might depend on the composition. Right?
So I think the difference from the magnetization problem of the velocity and the polarization is something to note. Here you can have a non-zero velocity even at the equilibrium T, when T is at Tn.
Because of the curvature.
In a planar interface, the velocity can be non-zero even if T at the interface is Tm, you are at equilibrium, but it's not so in the magnetization problem, where H has to be 0 for the planar interface. Now this comes in because the motion here is due to something else, the motion here is due to, and you saw the equation before, this is justified.
So I've wiped it out. Yes. So that's a good remark. It's the difference between diffusion controlled reactions and interface controlled reactions. But so indeed, as I have told you, these interfaces here between two phases of different energy content or different composition, they have this conservation law which is expressed by the Stefan condition. So in fact, the interface motion is conditioned by the fact that you have a current. So without a current, you cannot move. Okay. Here, in substances like metals, this value of mu k is very large, usually. So the interfaces relax very quickly to the equilibrium. So if you have a current that is weak, so you have a slow growth process, that means that indeed the interface will always relax to its equilibrium position, and yet it will move because it is fed by the current. It's a good example. Whereas in the magnetic model, where you have only the action of the magnetic field is on the interface directly, then you need a finite magnetic field to make the move.
Okay, so then we'll break for coffee.